At the organic compounds and structures, and these are different functional groups. We'll learn a few of them. I'm not going to get into detailed organic chemistry. I'll show you where you're going to be going in the next semester, those that are going to take organic chemistry, and Dr. Jones will lead you through organic chemistry. So these are just some of the topics in here. Last semester in 1A we talked about alkanes, we talked about carboxylic acids, and some alcohols. So we're going to toss in a whole bunch of other functional groups. And the thing I'll be more worried about, since my major is physical chemistry, and I had to take organic chemistry and I hated every minute of it. One of the things, they try to make it more interesting now, but that was back then. So I started taking as many physical chemistry courses as soon as possible, and analytical. Talk about organic compounds. There are different ways of representing them. This is the way we draw things on the board. There's even a more modern way, which this book doesn't mention too much, but you see more and more of it. I notice when Dr. Jones is talking to his students, he uses it a lot. We do a carbon chain, 1, 2, 3, 4 carbons. And then if you don't have anything else, there are hydrogens at each of these points. And carbon has I'll talk about the hybridization in a minute, different hybrids. But these are just different organic molecules. And they get more and more complex. Down here you see something that looks like a steroid or something. Testosterone is what it is. So this is the structure. These are the ball and stick models. And one of the things I'm going to say, we're not going to get to anything this complex. We may mention it briefly here and there. And this is the space filling models. These are all different things we talked about. Organic chemists are big on structures and molecules. And there's some more hydrocarbons. We start off with the simplest one, methane, ethane, propane, functional groups. I was looking to see if I had the table that you have to start off with. I don't have it in this slide. Okay. Now, one of the things that makes organic chemistry complex is that carbons bond to themselves. Okay? And if you have a 1-carbon chain, the prefix that represents 1 carbon is meth. That's what you have to learn. It's a table way back. I think I must have one set of slides. Let's see what else I have. Because it's way back in chapter 3. There. So I'll do the table myself. We have a 2-carbon chain. These are the prefixes that say you have 1 carbon, 2 carbons, 3 carbons. Bute or but, whichever way you want to say it. And my joke at this point is, organic chemists wanted to be unique, so they did that, but they lost all their ingenuity because when you get to 5 carbons, guess what they use? And so if you know all the other numerical prefixes, you know what comes after 4. Okay. Pent, hex, hep, octanol, dec. And I did dodeca a few minutes ago, and I always say I don't really like to memorize those either. And so if I have, first of all, when I'm asking you to do structures and things for me, I don't want to count up past 12 because I ran out of fingers, so I probably won't go past 10 for most of my structures. So all I have to do is know the numerical prefixes up to deck. if I really want to put something fancy, like 20 carbons, I don't even want to count 20 carbons, but if I did, I'd tell you what 20 carbons meant. Okay. All right. Okay. So anyhow, that's the first thing. And these are the prefixes you should know. After that, we have other prefixes, but I mean not other prefixes, they're the usual prefixes we already know from Greek numbering systems, okay? And then we have the word ending, which is going to be determined by the functional group, or it'll tell you what the functional group is. Now, there are a lot of different functional groups in these organic molecules, and they can act independently of it. We aren't going to get anything that complex. But the two things about functional group, they, one, determine the name of the molecule, and second, when you're doing chemical reactions in organic chemistry, the functional group, no matter which molecule it's in, sort of reacts the same way under all conditions. It may react slower or faster depending on the molecule, but the functional groups determine the types of chemical reactions that occur. We already talked about carboxylic acids in 1A. Carboxylic acids are the organic acids. First of all, they're going to be weak acids. We saw that when we were doing acid-base nomenclature. And the other thing is, no matter what type of molecule it is in, it'll react with a base to make a water and a salt. Okay? Sometimes it's protected so it doesn't react very rapidly, but you can make it react if you work at it. So the functional groups have two important reasons for being. So you have to know about this, because you start with this and you add a word ending. And then you have to put prefixes and all the rest of that, so the functional group determines the word ending. Now we start talking about functional groups. The simplest molecules are, and we're going to talk about hydrocarbons first. They have hydrogen and carbon. Now when you're doing the condensed formulas, you always put carbon first because organic chemists, the joke is, if you know about 6 elements, you know everything there is to know about organic chemistry. You know about carbon, hydrogen, oxygen, nitrogen, and then sometimes you throw in some sulfur or phosphorus, and you're done with organic chemistry. You don't need the rest of the periodic table. Okay? So we're going to start off talking about hydrocarbons, and the simplest member of this is referred to as the alkane functional group. The word ending here tells you the word ending that goes with this molecule or with this stem. This is the numerical prefix, or the stem that tells you how many carbons are present, and then you add A, N, E. They have a general formula. They sometimes refer to this as a homologous series, and they like to make it look mathematical and scientific, so they talk about homologous series. So if you have 5 carbons, you know it's a pent, and the general formula, 2n is 10 plus 2 is 12. So you know that's pentane. This is called a saturated molecule because there are 4 single bonds to the carbon. So let me go back to that other slide where it was. go. So the simplest member for the alkanes is a 1-carbon chain, 4 hydrogens. I don't know how you write it in this particular way of doing it, because I didn't study that. This looks weird to me, but that's the only thing I could say they would do. Because there's a dot with 4 bonds on it. I don't know if they do that, I just make some of these things up. So this is what I would expect to see, or CH4 is the condensed formula. I won't expect you to draw these, but I brought my model kit. That's the tetrahedral structure. And this is an old-fashioned set. The reason you know it's old-fashioned, nowadays hydrogen is white, but in the old molecules it used to be yellow. Okay? I don't know why they changed the color. So this is my carbon atom. Somebody drew in or drilled some holes in here at 109.5 degrees apart, or 109 degrees 28 minutes, whichever number you like, or 109 degrees. Boy, these carbons are slippery today. So this is the structure he's referring to up there, and he used the modern color in this textbook. So he has the white hydrogens on there. And there's our tetrahedral structure, and all these bond angles are the same, and that's what this thing represents. When I'm looking at your answers, first of all, for methane, I'm not going to ask you about that. But usually, we don't worry about putting in the hydrogens, we only put in the non-hydrogen things. Since we're doing hydrocarbons, that's all that's left to do. This over here. This is what you would do in this thing. Because what you have is a 3-dimensional structure. You're trying to put in a 2-dimensional blackboard. And that's what you're trying to represent here.
Is the ending E and E because of the double bond?
Yeah, I'll get to it. I'll do that in a minute. But while I brought this, I carry this stuff around once or twice a year. And one of the things that happens, the reason I'm going this far, is the carbon-carbon single bonds have free rotation. So these things are rotating. You can put these on the board in any direction. You put it like that, you can put it like that, or you can put it like that. You see all sorts of structures there. Because they freely rotate about the single bond. So when you want to do a 5-carbon chain, this 1, 2, 3, 4, 5. That's because I didn't have much space on the quiz, so I sort of squeezed it together like that. Or I still have trouble with this. 1, 2, 3, 4, 5. That's the easy way. The reason they like this is because computers can draw those really fast. They can put things at different angles and do the zigs and zags in a second. But I'm used to do this. And of course, then, since this is an alkane, you have to put in your other bonds. Because sometimes, whoops, what's wrong with this one? I didn't have enough bonds there. So sometimes I'll ask you to put in all the bonds, so you have to remember to put them in. The other times, I'll just say draw structure. And all of these things are all different ways of representing pentane. The easiest one, of course, is we have pentane. Didn't do that in 3 seconds. Then, next thing we talked about saturated or single bonds to carbon. By the way, and I'll come back to this when I get my other set of slides. That's an sp3 hybrid orbital, if you remember that terminology from 1A. We introduced you to a little bit of hybrid. We introduced you to the discussion of hybrid orbitals. It's a combination of an s orbital and 3 different p orbitals. Okay. I also use this terminology a little bit. Back in the beginning of the semester, we were talking about the geometry of these complex molecules and complex ions. Okay. So in a saturated alkane, this is going to have sp3 hybridization. Now we're going to run into the next thing. Again, as a physical chemist, I can deal with this.